IBM CEO Arvind Krishna comes to the World Economic Forum fairly regularly to comment on topics like AI and especially quantum computing. In the past, he gave dates about when we should expect quantum computing to be available, but the timeline is not always right. Nevertheless, there seems to be no doubt that quantum is around the corner. Arvind Krishna gives an update about quantum computing during a panel at the World Economic Forum 2026. However, some of the aspects of quantum and AI presented in previous editions of the forum are still valid and give a bigger picture of the new technology. Here are his comments.
We're still on the timeline, so we're at 400 qubits today. That's on the cloud. You can go ahead and use it. By the way, a real quantum computer, not a simulation, not something virtual, a very real one.
Wait, 400 qubits?
Yes.
That's a big deal.
433 qubits today.
Okay.
1,000 qubits end of this year. You can solve problems in material sciences. Imagine lithium hydride for electric car batteries. Imagine fertilizers. There was a paper from China recently which said at 400 qubits, you could probably break today's encryption. I'm a little skeptical of the full validity of that paper, but okay, fine, 400, maybe 1,000. So that tells you that somewhere around 1,000, you're beginning to see problems being solved that you just couldn't imagine getting solved on what I would call classical computers. Quantum is not going to replace classical, just to be clear. You're not going to run your bank balance on a quantum computer because a quantum computer may give you a different answer each time. For some things, you likely want the same answer. But the physical world, materials, chemistry, encryption, optimization problems is what I believe we'll see some of them getting solved in this time frame. So I'm still there, and the progress made is that now we have 400 plus real. We have been out there for the last 10 years. We have actually been working on quantum proof encryption. We put it out as open source. We work with NIST in the United States, who have 4 what they call preliminary standards out there based on collaboration from us and from many, many other people in the industry. And I would strongly urge everybody that for the data you really, really care about, that if you encrypt it, put it on a tape, throw it away, and if in 10 years you're worried somebody might decrypt it, go use quantum proof encryption now. Because even stuff that you store will get broken, and if it's going to embarrass you, beware. I first have to acknowledge, maybe you covered it before I came, but Dr. Martinez deserves a lot of credit for the work going back all the way to his doctorate and first postdoc, because the technologies that I believe are going to bring useful value to this room were first invented out of his early work. And many, many others, including us, have built on that work since then. So let me just begin by saying that. Look, it is not yet commercial because we are not yet at a scale that can bring a lot of useful value. We can see it around the corner. We can debate is that corner 2 years, 3 years, or 5 years. I'm probably in the middle of that. Some others have said 10 to 15, and then they had to walk their words back. That maybe it's closer than that. The reason always is you have to first convince, and I think it's authentic, that the science community, not every scientist, but let me call it, the science community should be convinced that this completely new form of computing, and I try to strip the esoteric language out of it by saying, look, it does a third kind of math. Normal computers do, I'll call it a little bit superficially arithmetic, but let's call it algebra. GPUs or AI do matrix math. These do math on which, the math was actually invented before quantum mechanics came, around Lie algebras and math like that. So these are going to do that. So the question comes to, when will we have the scale on which you can do something that is unlikely that a classical computer can do? I think that moment will come in 26 or 27, so it's not that far away. That doesn't yet mean that it is cheap enough and you can do it with enough repetition, with fewer errors. So then another year or two to reach that point. So I actually believe that the path from now, not to the end, not to the eventual quantum computers, but to the first ones that have incredible commercial value, is an engineering path as opposed to science. When I say science, I mean, do we know how to take quantum states meters away? That's a science problem. We think we can do it, but we don't quite know how. Can we confine it, as Dr. Martinez said, to one semiconductor, maybe in one cryostat? Yeah, we think we know how to do that. So to make that work is engineering. And as I think the world has realized, when it's an engineering problem, those with enough grit, the expense, the talent can usually get there.
Okay.
When it's a science problem, then you need science to be, maybe discovered is the right word, maybe invented is the wrong word in science. I don't think anybody is benefiting now. I think people have concluded they can benefit when we get to this. I have held a very strong point of view. Number one is going to be simple materials. Let's call it simple molecules. Molecules with a couple of hundred electrons or less. So think maybe lubricants from fuel. Lubricants are very important because they can reduce the amount of energy needed. Today we get 30% of the oil out from an oil well. That's it. If you can get a better lubricant, maybe that can turn into 40. That means less drilling, less environmental impact, less lots of things. But simple molecules, maybe we can turn quantum computers to say, is there a better material to do carbon sequestration? Those are the kinds that will be number one. By the way, the materials industry is a multi-trillion-dollar industry. We're talking between 5 and 10, depending on how you want to call it. So even a 5% productivity advantage there could have massive. I hold a side hope. I'm not going to tell you this is a guarantee, that maybe we can invent better fertilizers. Fertilizers today are based on a process that was invented by a German chemist, I think in 1890. It's literally the same process. The Haber-Bosch process to sort of crack and make ammonia and then convert it to urea and nitrogen to fix nitrogen. We know bacteria fix nitrogen with photons. So we know there is an alternate biochemistry process that works. We have no idea how to discover it. Maybe we'll get there. So chemistry, I think, is one big area. The second one, which everybody's excited about, is problems in finance. So certain, not all, certain problems in finance, pricing of very complicated instruments, things when you put multiple constraints are very hard to solve through the current methods. Those are going to bring value. And the third area is around optimization. These, by the way, I stick to these three and not more, because in these three, the algorithms to do it on a scalable quantum computer are provable and known. In other areas, we believe we'll get there, but they're not yet known. A different appetite. I see half a dozen banks embracing it, figuring out internally. It's a 2-year journey from the time they get interested to when they learn, okay, this is a really different thing, how do I use it? Then they have to use their data to see, is it applicable? So now we're talking, that's a 3-year journey. Clearly, the vast majority are waiting for that first moment. That means they'll be 2 to 3 years after that. So it kind of points to the timeline you just laid out. When it's an engineering problem, you can debate because of competition, because of other things, you're going to keep it more protected for some amount of time. The science problems, of which there's an infinite number, I really would encourage academia to work on those, which are beyond sort of the 2, 3, 5-year roadmap. And there's a huge number of those. So, look, making a quantum computer is a lot more than just a qubit. I actually think that, unfortunately, that word has been latched on mostly by the media, so it becomes the mnemonic. You've got to think about, it's not just a qubit. How do you control the qubit? I actually believe that a more perfect qubit is going to be harder to control, because if you can't change its state, which is why it's perfect, how the hell do you control it? You got to have them interact with each other. So there is a golden mean somewhere that each of these technologies has to get to. All right. But now you have to think about, what are the materials? What is your semiconductor process? What is your packaging process? What are your cryogenics? By the way, there's a lot of controls that come out of normal semiconductors that help you manage all of these. What is the software that is going to make it easy for people to access these machines? You just mentioned algorithms, which then becomes the equivalent of what we call libraries in today's computer world. You got to think about, is this machine self-tuning because we know that the coherence time is at milliseconds or seconds or minutes, it's not more than that for the foreseeable future. Does it get back to a state which can be used? You got to have this whole collection of technologies. The piece that we're talking about, which is it, is just one out of these 10 pieces. We have bet on this because when we looked at this, we believed that the low or the cryogenic temperature just above absolute zero, superconducting, which is a macro architecture as opposed to a micro at the atomic level architecture, is going to make progress the fastest, is the most controllable, and actually can be manufactured at scale in a current semiconductor process. The advantage of that should not be ignored. Now, we could be wrong, but the other 90% of the work still applies, and we would be very quick if we realized that some other approach is correct to either bring on those engineers and scientists or work with them because we have a lot of other capability. So yes, we are making a big bet on one approach. I'm very clear about that. But that doesn't mean that we are completely blind to other approaches should they come. Most of the other approaches, people don't want to admit it, but they're 1,000 to 10,000 times slower. Oh, yeah. So unless they're 10,000 times better, the speed you get on the first approach is going to win. For some of the core technologies, when something could also be a weapon, as in decryption, then you actually reach all kinds of concerns around if you share, where do you stop the boundary? And I think it's impossible to stop the boundary, which almost prohibits sharing for some of the most critical elements at this stage of the evolution. Yeah. I just think that people forget about that. So most of us who work on it do get a lot of questions from government. They don't control us because they accept right now that we are self-constrained in how far we let the technologies go. But I actually think that if I think about algorithms, if I think about use cases, if I think about cryptography, if I think about safety, if I think about cryogenics, I think those are all areas where it's hard to assert that those should be constrained or kept to only one place. The cryptography that looks like quantum cannot crack is well known and well understood. It's based on a mathematics field from 30 years ago called lattice cryptography. And from everything that the deep cryptographers, not just in corporations, but in academia and in governments around the world have studied, that approach is valid. NIST ran a competition starting 10 years ago, 200 people submitted. They picked 4 out of the 200 that they felt good. I think that those 4 is a great starting block for the world to use. Now, when is that moment coming? Because people say, well, if it's going to be in 2045, I don't really care. I would assert that, not that I'm saying it'll happen, but people should be prepared that maybe by 2030, maybe by 2035 at the outset, nation states may have the capability. So what are you putting out that if somebody captures, they can't break today, but they could break, and if it is still of value in 10 years, maybe you should think about doing it now. Yeah. I think this is like a Y2K moment, but maybe smaller. Because these other alternates are not actually more complicated than the current. You just have to change. It's about, because it's a new kind of math, just like I would say we could predict AI coming in 2015, but it took till 2022 to kind of get there. It takes years to get used to the new kind of math and what could be of value. Forget, is there a quantum computer? Assume there will be one. So ask yourself the question, how long will it take? Who are my unique 3, 4, 5 people who can map between the old world and the new world? And they should then come to the conclusion of what use cases could be of value, learn how to use the quantum computers of today, which I admit are subscale, and then you're ready that when they come, you actually don't have to do that massive amount of prep work at that point.
Now, the topic of how to make the technology available for everybody was touched only briefly, but the principles discussed for AI back in 2023 apply also to quantum and to new technologies in general. Let's listen.
Let me take a different perspective completely. Let me take a completely technologist opinion to how do we get things to be much more inclusive and get billions to embrace it. One simple example from 30 years ago. When mobile phones first came around the globe, it cost $1 a minute to make a phone call when you were in the US or in France, circa mid-1990s. By the 2005 time period, countries like India and some countries in Africa were doing it for 1% of that number. So technologists have to go focus on how do you drive the cost down, not with a subsidy, still making a profit, but drive it down, because if you can bring it there, then the whole world can participate in those technologies and the benefits. So take AI. How can we make model deployment first, literally at 1% of today's cost? Focus on the complete stack. What is the power requirement? Why does it have to be so high? It's interesting. All of you are taking it for granted that it has to be so high. Nowhere is it written in the laws of physics it has to be this high. It can literally drop to 1% of what it is. I know, because Abdullah is investing in some companies like that, right? It is not just one player. There's many others. Two, when you look at model training, why does it have to take so long? Can one have alternate techniques? They proved one a few years ago, but there's many others that could be done. By the way, can you start with a base model and incrementally add what's needed for a country, a domain, an industry in a very small way? So the approach we will take is, let's focus on those aspects. Can I drive it down to be 100 times cheaper? I'll tell you, I have 30 times line of sight. I need 3 more. So the first big part is done. That will make it inclusive, and that is what will get it done. Then my hope is that these frameworks allow us to go work in each of these countries and industries.